And another word for dielectric is like an insulating material. Okay, so usually what a capacitor, let's see, this would be a parallel plate capacitor. So the capacitor can be made like this with air in there or vacuum, but then that's going to be a weak capacitor. We can call that an air capacitor. So usually what we do is we slide in some kind of dielectric in there. And that dielectric is an insulating material which is polar. So polar insulating material. I'm not going to go more into it today, but tomorrow I'll explain how the dielectric actually works. That's what we're discussing in this chapter, dipole moments, because we want to understand how the polarity of the insulating material can actually help make this capacitor better. So what the dielectric material will do is it's going to take the voltage across that. So if I have the capacitor disconnected from the battery, essentially, let's say I've already charged this capacitor to 1.5 volts, right? And now I've disconnected it from the battery, right? So now it's a 1.5 volt. It's actually charged to 1.5 volts. If I insert a dielectric in there, that's actually going to reduce the voltage, because the polar molecule in there is going to fight the electrical field of the external two plates. It's going to keep the charge the same, but the voltage is going to drop by a factor of kappa. So depending on what the kappa of that material is. So it's going to basically, the voltage of that plate is going to drop by a factor of the insulating factor of that dielectric, which means the capacitance is going to drop, is going to increase by that factor. So the capacitance of a parallel plate capacitor is going to be kappa A E0 over D. So we just add an extra kappa at the top. We can kind of look at some informal definitions here and get some pictures. Dielectric materials. Examples include porcelain, ceramic, mica, glass, plastics, and the oxides of various metals. Some liquids and gases can serve as good dielectric materials. That's interesting. Liquids and gases. Dry air is an excellent dielectric and is used in variable capacitors and some types of transmission lines. Distilled water is a fair dielectric. So you can see a whole range of different dielectric materials you can put. So you can see kind of some images here. So you see what's happening is the polarity of the molecule is aligning up so that, see here, this is a nice picture. You got a charged plate here, Q, you got a negative Q. So the electrical field it creates is this way. And then this polar molecule is flipping such that the negative of the molecule is facing the positive of the plate, and the positive of the molecule is facing the negative. So negative, negative, positive, negative, positive. And then therefore, this one is creating an electrical field in the opposite direction. So again, I'll go more in depth into that tomorrow. So here we can kind of see some other materials and their dielectric constants. silicon dioxide, 3.5, aluminum oxide, silicon nitride. So they're kind of in the range of 3, 8, 6, 29. So what happens? Those will tend to increase the capacitance by that factor. You know, so depending on if you want to make a stronger stronger capacitor. So you guys see how that's basically a bunch of parallel plates. So you're taking a plate, dielectric, plate, dielectric, plate, dielectric, but then you're just sort of rolling them up. So you're essentially just have, so it's kind of, I'm going to draw that for a second. I'm going to draw that here. You essentially just have this big sheet, right? Aluminum, right? And then another dielectric in between. So it's really a parallel plate. Then you have another aluminum. Then you have a dielectric. So you can make this at home. You have aluminum, so on, right? And then what did they do? Just roll this up. You know, basically take it, just roll it up, roll it up, roll it up, roll it up. And then that's what you get. And then basically, once you roll them up, then you can cut them into different pieces. Then where should the positive plate go? So essentially you are so this should be the positive. So let's just say this is the positive. And this is going to be negative. And this is going to be positive. Right? And then the next one is going to be negative, and so on. So actually this kind of connects to our very next topic, which is series and parallel circuits. So you're essentially creating what? Imagine connecting the battery to a bunch of capacitors that look like this. Ha-ha. C1, C2, C3, C4, C5. Right? And what are these? They're capacitors in what? Series, right? So that's the next topic. We're going to learn how the capacitors add up in series and parallel, right? So this is in series. In a series construction, you're basically saying the charge goes like this, builds up positive here, then this is negative. So you see, then you have a dielectric in the middle. You see? Then, hold on. Then between that dielectric, so this one kind of acts like its capacitor. All right, and then this is positive. This is negative. So the positive of this capacitor touches the negative of that capacitor. And then this one has a dielectric in the middle. And then a positive of this and negative of this. So it kind of acts like this. Positive, negative. Then the positive of this touches the negative of this. So this one acts as another capacitor right here. You see, positive, negative, positive, negative, positive, negative. Positive, negative, positive, negative, positive, negative. Right? And then, so if I want to touch the leads of the positive to here, and the negative should touch to the other one. You see? So, in other words, here in the video, let's see here. This one should touch where? Let's say the positive. This one should touch this outer aluminum, you see? And then the other one should touch all the inner one, basically. The innermost aluminum is going to be the other side. So you just need one on the outer one, this one on the outermost one, and then this one on the innermost one, and then you're set. Basically you made a complete circuit. Okay, so now that we established that the dielectric increases it by K, and then let's jump right to the series and parallel topic. Okay, so then how the capacitors add up in series and parallel. Okay, capacitors in series are going to add up like this, right? So the idea behind series is that the charge induced on this plate is going to be the same as the charge induced on that plate and the charge induced on that and that and that. So then you're going to have the Q's are going to be the same. Q1 equals Q2, which equals Q3, which equals Q4, so on, so on, so on, which equals to the total charge that is stored in the whole system, the charge that's flowing through the battery. And voltage of each one adds up. Voltage of 1 plus voltage of 2. I kind of talked about this back when we did conductors in series, right? Thermal conductors in series and thermal conductors in parallel. So remember I said always something is the same and something adds up. So in thermal conductors, it was the heat that is the same, the heat flow. And then what adds up is the temperature difference, right? The temperature difference of this plus the temperature difference of this. So voltage acts like temperature difference. V2, V3, V4, V total. So then let's use always this relationship, Q over V. So remember the definition of capacitance was Q over delta V. But remember, when we write V, we actually mean delta V. So I'm not always going to be writing delta V. V means the voltage difference between any two plates of a capacitor. So it literally does mean delta V. Okay, so then V will be written as Q over C. Okay, so then we could say Q1 over C1 plus Q2 over C2 plus that equals Q total over C total. And then the Q's cancel because they are the same. And then so we get 1 over C1 plus 1 over C2 plus 1 over C3 is equal to 1 over C total. So capacitors in series add up such that their inverses add up to give you the inverse of the total capacitance. So it ends up that the net capacitance of a bunch of capacitors in series are less than each one by themselves, right? So in other words, if each of this had a capacitance of 10 microfarads, 10, let's say you had 5 of them, what would be the net capacitance of that? 5 of those aluminum sheets with the dielectrics, right? So let's say you have all 10. It will kind of be equal in the case of the making capacitors, because remember they're using the same material for each one, and the plates are the same size. So it kind of makes sense that they would be identical in that case. right? So if you had 5 identical ones, what would happen? 1 over 10, 1 over 10, 1 over 10, plus 1 over 10, plus 1 over 10. What would be the net capacitance be? Let's see, what is that? 1, 2, 3, 4, 5. 5 over 10. And then which would be 1 over 2. And then the net capacitance would be, so remember, after you get the answer, you get 5 over 10, you get 1/2, but then you have to reciprocate it again. You have to reciprocate both of them. So then C total is 2 microfarads. So then 10 microfarad capacitors would be 2. Okay, basically this ends up always becoming less than each one alone, right? Which is 2 microfarads. Okay, how about in parallel? The opposite is going to happen, right? How is a parallel construction look like? So you can have a bunch of these in parallel to make a bigger capacitor. They actually end up adding together. So what's the same and what adds up in a parallel construction? So then in a parallel construction, you have the voltages add up. No, sorry, the voltages are the same. Okay, but then the charge adds up. So this battery gives this guy a certain charge, gives that guy another charge, give the other one another charge, because the charges come and they split up. They split up into different capacitors. So then the charge says Q total is Q1 plus Q2 plus Q3 plus Q4 plus that. Right? Then I use the relationship between C, Q, and V. So whichever one adds up, I solve for that. So then I say Q is equal to CV, right? And then I'm going to say Q total is equal to C total, V total. Q1 is C1, V1, plus Q2 is C2, V2. And then I'm going to argue that the V's cancel. And then the capacitance, this was so much easier to derive than for thermal conductors. Series and parallel, that's it. This is series for capacitors, and this is parallel for capacitors. And then in the next chapter, we'll derive how resistors add up in series and parallel. So those ones are actually quicker than the derivation for the heat resistors, the heat conductors in series and parallel. Much easier. Which kind of this leads me to ask, well, then why would they even build a capacitor like this? In other words, is it advantageous to you? So imagine, let me give this as an example.